Uh,
Okay.
So I think it's time. So maybe just 1 minute and we can start. Okay, so let's start. So hi everyone, thanks for coming to today's one word seminars. So it's our honor to have Professor Zhao from University of Pittsburgh to present his recent work on heteroskedastic sparse PCA in high dimension. So Dr. Zhao is an associate professor in the Department of Statistics at the University of Pittsburgh. He got his PhD from Yale University in 2014, and his interest in mainly on high-dimensional statistics inference, graphic model, precision metrics estimation, robust inference, and he have done many work in those direction, and also have some application in the statistical genomics. So Zhao, take the floor.
All right. Okay. Thank you. Thank you for the kind I would say invitation and introduction. So it's my great honor to present my recent work here at 1W-MINDS seminar series. So today's talk is about a PCA. It's a very classical multivariate analysis tool. But today I want to talk about some new interest in this area. So this is a joint work with my students Rhea and Pei. Okay. So I will start from some basic introduction of the PCA problems and the challenges in high dimension, as well as the additional challenges with the heterostatic noise. And the major contribution of this talk is we proposed a real optimal algorithms based on a very classical numerical analysis tool called power method or orthogonal iteration algorithms. And our algorithm involves two parts, and we will talk about details, and each part is critical in the analysis. And to justify how our algorithm is useful and it's really good, we provide corresponding theoretical guarantees. So in particular, we provide the rate convergence for our algorithms under some mild conditions. And also we provide a matching minimax lower bound to show that if we consider the min-max criterion, then our procedure is minimax optimal. Okay, and in the end, we want to talk about some extensions, applications. Also, I want to talk about the interesting application in the single cell RNA sequence data classification problems. Okay. All right. So PCA is a very classical multivariate analysis tool. So if you look at any textbook on multivariate analysis, so PCA is one of the topics for sure. Okay. So the first PCA or principal component actually is just the direction such that the projection of a random vector retains the largest variance. Okay, so it can be coined as the optimization problems. Okay, here. Of course, this dimension reduction interpretation can be generalized to the multiple case. Right? So the multiple PC can be solved by maximizing not a single variance but the trace. Okay, and given the constraint that each PC are orthogonal with each other. Okay. So if we know a population covariance matrix, sigma is given for the random vector X, and then the PC, we can calculate the PC just by doing the simple eigendecomposition. Okay, actually the leading eigenvectors give you the leading PCs. Of course, in practice, we don't know the population covariance matrix. So what we do is we just calculate the sample covariance matrix, right? That's very simple. And we do the eigendecomposition based on the sample covariance that give us the estimator of the leading PCs. Okay. So in the classical low dimensional setup, in the sense that dimension P is fixed while the sample size n goes to infinity, then we will get asymptotically normal estimator. So this is well known textbook result. Right? Okay. However, in high-dimensional setting, in the sense that when the dimensionality p over n doesn't go to 0, then the classical eigendecomposition approach would fail. Okay. So actually, in a very simple model called Sparse model we will discuss later, on those people in the literature show that by doing that decomposition we get inconsistent estimation. In fact, without any additional structural assumption, there's no hope to get a consistent estimation in high-dimensional settings. Okay, so that means people have to impose some structural assumptions in high dimension. And the sparse PCA or sparsity is one of the most popular assumptions, structural assumptions. Right? So people assume that the leading PCs are kind of sparse in the sense that many coordinates of the leading PCs are 0. Okay, so due to the sparsity, there are a bunch of algorithms and methodologies were developed. For example, Zhao et al. And Witten et al. They proposed use the regularization with lasso penalty and to induce the sparsity. Okay, and also other researchers consider the convex optimization approach, such as the very famous the Fantope algorithm. And there's a line of research and they applied where they are rooted, the approach were rooted with the so-called power method, which is the key for our proposed algorithm later. Okay, and also on the sparse PCA not only can give us consistent estimator, it also has a very good interpretation. So here the interpretation means in the original classical PCA, the leading PCA or the estimator, PCA estimator may involve too many variables, right? And the sparse PCA actually tells you which variables are most important compared with others. Okay. And during the last 10 years, there's a bunch of works were devoted on the theoretical guarantees. Right? I just list the 3 papers, and they provide the optimal rate convergence for estimating the leading PCAs, including the lower bound, and for slightly different models. Okay. To study the sparse PCA, it's natural to look at one simple model called spec covariance model. So the spec covariance model assumes there's a spike on the spectrum. In other words, there are only a few eigenvalues are strictly larger than 1, while the remaining eigenvalues are equal to 1. So in Johnston, in the 2001 paper, they used the phenome data as a real application to illustrate that the spec covariance structure. So if you look at the third here, this is the script plot, and you see that there's a leading, this is the plot for eigen values. So there's a 3 eigen or 2 or 3 eigenvalues are above the remaining eigenvalues. Okay. So for the remaining values, they look at similar with each other. Okay. So for the spec covariance model, actually, the covariance can be decomposed as 2 parts, right? So the one part is proportional to identity matrix. Okay, so previously I just talked about 1, but this can be generalized to sigma square. And then there's a low rank perturbation matrix. Okay, let's assume R is a given number, a small number, and there's a few spikes, which is lambda 1 plus sigma square, lambda 2 plus sigma square, and lambda R plus sigma squares. That's the leading eigenvectors. Okay. Under normality, actually, this model we can rewrite or represent each observation xi decomposed as the sum of 2 parts. Okay, and the epsilon I is the noise, and we assume the covariance matrix of the noise is proportional to identity, right? So it's the second part, and there's a latent variable, and latent variable has the intrinsic low-dimensional structure. In other words, if you look at the covariance of Si, it has the low-rank perturbation matrix. So here the lambda j in decreasing order is the eigenvalues of this low-rank matrix, and the corresponding eigenvectors are Ui. Okay, so questions so far about the model backwards. Okay. Recently, there's some reason to believe that one should not always assume the noise, each coordinate of the noise have the same variance. In other words, people believe it makes more sense to relax so-called the homostatic noise assumption. Instead, people allow different coordinates of the noise have different variance. In other words, we allow this heterostatic noise structure. Right? So this is called a generalized covariance model and was originally proposed by Yu and Yu et al. In 2015 papers. And there are many applications, including the sequence data and the imaging data, and as well as some network analysis. Okay. Of course, people have to be cautious when allowing such extension. Right? So without any additional constraint, let's say this simple example, the same covariance matrix sigma can be decomposed in two different ways. Okay. In each way, the first matrix is a low rank matrix. Actually, this is rank 1 matrix. Right? And the second matrix is the diagonal matrix. Okay. So, but there's two different decomposition. And if our goal is to recover the eigenvector of the low rank matrix Ui, so the first decomposition gives you the U is equal to 1, 0, 0, 0, right? So it's the canonical basis, the first canonical basis, and the U in the second decomposition actually is the second canonical basis. So they are not only different, but actually they are orthogonal with each other, right? So this is the well-known identifiability issue. So to avoid such identifiability issue, here we adopt a concept of the incoherence condition. And of course, other conditions such as delocalized condition can be proposed. Okay, so but they have they're based on the same idea, right? This incoherence condition was originally proposed by Candice and Tao in 2010, 2009. So intuitively, that means, if our goal is to recover the leading eigenvector of the low rank matrix U, then the U should not be well aligned with any of the canonical bases. For example, if you look at the first decomposition, and this U is perfectly aligned with the first canonical basis, so this incoherence, so this is a defined incoherence constant I of U can be very, very large. The intuition is if it's well aligned with the canonical basis, so we can move this to the second component, diagonal matrices, so that you can now tell apart this low rank matrix and the diagonal matrix. So by definition, this incoherence constant can range from 1 to up to P over R. Okay. When P is very large, this range is quite large. Okay, so here later we impose some condition in terms of the incoherence constant, and we impose very mild condition, and so that the identifiability issue can be avoided. Okay. In other words, okay, the smaller the incoherence constant is, the better we can avoid the identifiability. Okay. Actually, in the last 2 or 3 years, this problem was carefully studied in the relatively low dimensional setting, in the sense that dimensionality P cannot be larger than the sample size N. So this was first started in 2002 by Andrew Zhao and his co-authors, and they provide an optimal algorithm based on the newly developed robust perturbation theory. And later, Yan et al. From Princeton University, they take one step further. They provide a statistical inference of the leading eigenvectors. And also they consider the data can be missing at random. Okay, so our, this talk or our work is different in the sense that we consider high dimensional sets. In the sense that we allow P is larger, can be far larger than the sample size N, but we consider additional sparse structure on our goal, which is the leading eigenvectors or pieces. Okay. So here we assume the leading pieces U at most S number of non-zero rows. Okay. So in other words, we define the sparsity as the row sparsity on this U matrix. I want to mention that in this work, theoretically, we assume the little r, the rank of the low rank matrix is fixed number. Therefore, if we impose the sparsity in terms of the row sparsity of U or the entry-wise sparsity, there's no big difference because the column number of U is r. Okay. And there's another a line of research directions also called heteroskedastic PCA, mostly in the computer science community. So I just listed 3 conference papers by Hong et al. And they consider the heteroskedastic PCA in an alternate way. So they consider within each samples and the noise among different coordinates are uniform, but across different samples, the noise of the variance on the noises can be very different. In other words, their setup doesn't allow IID observations. Okay, while our heteroskedastic PCA, we assume IID observations, but within each sample, each coordinate have a very different variance. So it's quite different setup, although both are called heteroskedastic PCA. Okay. Let me pause a little bit. Questions so far?
It's good.
Okay. Maybe I want to talk a little bit about the relationship between this PCA and factor model, because factor model is very useful, and also many people consider high dimensional analysis factor model in high dimension. And the key difference between the heteroskedastic PCA we consider here and those work on high dimensional factor model is that for factor model, usually people can estimate the factor loading matrices well based on there's a gap between the noise and the signal. In other words, as long as the signal is strong compared with the noise, they don't need the noise matrix is diagonal. They can allow heterostatic noises on the noise matrix, or they even allow non-diagonal structure for the noise covariance matrix. But here, instead of assuming the signal is stronger compared with the noise, here we allow any relationship between the signal and the noise. The signal, what I really mean is those lambda leading eigenvalues, and noise is the signal 1 to sigma p. Okay? We allow any relationship between lambda and the signal. All right, let's talk about the methodology or the proposed method. As I mentioned at the beginning, Okay, so let's just recap, right? So far, what we talk about. So we assume we observe xi, but xi can be written as si plus epsilon I. Of course, those latent variables and noise are not observed. Okay, and we allowed heterostatic noise for the noise vector epsilon I, and our goal is to recover or estimate the leading pieces of the latent low rank matrices, which is U1 to U. Okay, because we allow P can be larger than N, we impose the sparsity condition that the number of non-zero rows of this target U is no larger than, for example, some small s. S can grow together with N, but typically smaller than N. Okay. Of course, for statistical problems, we need to provide some loss functions to measure our estimation error, right? Because the U is an orthogonal matrix, is invariant under orthonormal transformation, so our loss function should be also invariant. Okay, so here we consider the projection matrix. The projection matrix spanned by the columns of the leading pieces. So not only this loss function is invariant under orthonormal transformation, but also it has very good geometric interpretations. Actually, it gives you the canonical angles between the space spanned by the truth U and our estimator hat. Okay, so here I didn't specify this the norm here used here. It can be the Frobenius norm, and or it can be an operator norm or spectral norm. There's no big difference because theoretically we assume the rank of U, which is RE, is finite. Okay? So in terms of the rate convergence, there's no big difference. Okay, so I want to talk about the very simple orthogonal iteration algorithm or the power method. Because our algorithm is rooted from these very simple algorithms in the textbook. Right? So for example, if our goal is to estimate, for example, the first eigenvector U1, right, of the matrix A. Okay, so the algorithm is very, very simple. So suppose we have some initializer U0. Okay, and we multiply U0 from the left by A. Yeah, and we call it a U1 bar. Because U is a univector, so we after the multiplication step, we normalize our estimator and to get U1. Okay, and then we repeat this multiplication and the normalization again and again until convergence. Okay, and why these simple algorithms can give us the leading eigenvector? So let's do a very simple calculation, right? So assume our initializer U0 can be, say, decomposed according to the basis U1 to UP. Because U1 to UP, there are orthogonal and univectors, so they form a basis. And the AJ is the corresponding coefficient for UJ. Right. So as long as A1 is not 0, after the multiplication step, we see that the coefficient corresponding to U1 is enlarged by lambda 1. It's enlarged the most because lambda 1 is the first eigenvector. Well, all other coefficients are enlarged smaller compared with the first. Right. And then after the normalization, because we know that all the coefficient delta norm has to be 1, right? So after normalization, and we do this again and again, and we see that the first coefficient will go to 1, while all other coefficients goes to 0. Right? In the end, we will end up with our leading eigenvector. So it's very, very simple. So we only need assumption that our initializer decompose, or only need our assumption that initializer is not orthogonal to the U1. In other words, A1 is not 0. Okay, so we will see that a similar phenomenon applies to our algorithm for the more complicated heteroskedastic sparse PCA problems. Okay, questions? All right, actually, this power method can be modified to handle the homostastic sparse PCA. And this was carefully studied by Zhongming Ma, and based on this 2013 Annals of Statistics paper. So in that paper, Zhongming considered the spec covariance model, but he assumed homostastic noises. Okay, and although the goal, of course, is the U, okay, and the U is also the leading eigenvectors of the the population covariance matrix, because it's the PCA problems, right? So we don't know the population covariance, but it's very natural to use the sample covariance because at least it's unbiased estimator of the population covariance matrix. Right? So Zhongming use this sample covariance matrix in the power method. Okay, so they have some initializer, and then they multiply by the sample covariance matrix. And this is the multiplication step. And then because of the potential sparsity, and Zhongming took the advantage of this sparsity by using an additional so-called thresholding procedure. I think the idea is also kind of straightforward, right? Because we know U is sparse, the true U is sparse. In other words, many coordinate of U is 0. Right? So after one update, we believe this U is closer to the truth, right? So that means many coordinate can be small. If it's very small, then we threshold to be 0. Okay, it's very large, and then we will keep as it is. Right? So this is a very natural idea. So by taking advantage of this sparsity structure, and Zhongming proposed another thresholding procedure. Of course, after that, they do the normalization. Right? Okay. And for multiple PCA case, the normalization is also called QR decomposition. Okay, and the thresholding procedure depends on the entry-wise threshold function. And actually, the paper proposed use the hard thresholding or soft thresholding or any thresholding functions sandwiched between those ones, including the well-known scat thresholding functions. Okay, so what matters most is not which thresholding function used, but the thresholding level. Right? So the thresholding level gamma means if the entry is below gamma in magnitude, then we replace it by 0. Right? Otherwise, keep it as it is. And the theoretical, I would say the justified thresholding level was proposed in the paper. So here, a gamma naught actually is some constant. Actually, it's just a constant 2 or any constant larger than 2. And the sigma is the homostatic noise on the noise level. And the lambda k, this is applied to the case column. So in the literature of sparse PCA, usually we assume lambda 1 to lambda k, the signal eigenvalues of the low rank matrix are comparable. In other words, we assume they are the same order. If we assume they are the same order, then this thresholding level becomes a uniform thresholding level. In other words, the threshold each entry of this U are using a same thresholding level. Okay, and then that is how they modify the power method or orthogonal iteration to handle the sparsity in high dimension. But what makes the model more complicated is the heteroskedastic noise. Okay. So here the difference is our noise matrix diagonal, but can have very different variance across different coordinates. Okay. So this will impose the challenges due to that our goal is the U, which is the leading eigenvectors of the low rank matrices. If the diagonal matrix is not proportional to identity, then the U is no longer the leading eigenvectors of the covariance matrix of X. This is quite different from the homoscedastic PCA, right? So homoscedastic PCA, that means the leading eigenvector of the X is also equal to the leading eigenvector of the low rank matrix of our target U. But now this is different. So, but we only have access to observation X. We don't have access to the latent variable Xi. Right. So if we only use some estimator of sigma, for example, sample covariance matrix, and to get the leading eigenvectors, then we will get inconsistent estimator because there will be intrinsic bias. So having said that, the sample covariance matrix of X is not completely useless, right? So now we take a closer look. We zoom in, look at the diagonal entries and off-diagonal entries. If we look at the off-diagonal entries of the sample covariance matrix, and we use the notation delta to denote, we just remove the diagonal entries or replace diagonal entry by 0. So this is off-diagonal part of the matrix sigma hat, then it's unbiased estimator of our low rank matrix sigma naught. So this is the key observation. Right. The bias actually occur or incur due to the diagonal entries. Right. So if the D of sigma hat represents the diagonal part of the matrix, sample covariance matrix. So this part, the sample covariance, sorry, the expectation of this part is not equal to the diagonal part of the low rank matrix. So there's a bias due to the diagonal entries. So that means we may still use the off-diagonal entries to get some estimate to get estimator of off-diagonal entries of the low rank matrix sigma naught. And we may use other methods or develop other methods to estimate diagonal entries of sigma naught. Actually, there are two slightly different approach in the literature. The first one is called diagonal deletion. So first proposed by Florescu and Perkins in the context of bipartite stochastic block model. Okay, so they propose that instead of using the bias the diagonal entries in the covariance matrix, they just simply replace by 0. In other words, they only use the off-diagonal entries of sigma hat to estimate the low rank matrix sigma naught. We know that this is not good, right? The bias can be alleviated but not completely gone. You replace diagonal by 0, still there's a bias on the diagonal entries. Okay, so Zhao et al. They took a step further, right? They call it diagonal imputation algorithms. So the idea is they use some other estimator, rough estimator of sigma naught, and they only use the diagonal entries of the rough estimator sigma naught. And together with the off-diagonal entry based on the sample covariance matrix, they take them together and get a better estimator of the sigma naught. Right? Because we have said that sample covariance matrix is still useful because we can use the off-diagonal entries. They are unbiased estimate. So they only update the diagonal entries from the sample covariance matrix. So our algorithms is kind of like a combination of those two different approaches, okay, together with the power method. So let's talk about details. So we need some input sample covariance matrix, right? And assume we know the rank of the low rank matrix R. Okay, and we have some initial estimator of the leading eigenvectors U. We talked about how to produce a reasonable initializer later. Okay, let's assume we have an initializer. And since our goal is the leading eigenvectors of sigma naught, but we don't have a good estimator at the beginning, so we just use the diagonal deletion scheme. Right? So our initializer, we just use the off-diagonal entries of the sample covariance matrix. Okay, and we'll use that in our power method. So we have the initializer of our estimator U0 and U0 hat, and we multiply U0 hat by our initializer of the sigma naught. Okay, and then we do thresholding, entry-wise thresholding, and after that we do the normalization. Okay, this is typical, right? So what makes our algorithm different is, in addition to the power method, after updating our target, the leading eigenvector U, we also update the sigma naught estimator. Because at the beginning, we only use the diagonal deletion scheme. We know that it's not good. Right? So after updating the eigenvectors, we do the projection to project the previous estimator sigma naught, the low rank matrix, on the space spanned by our newly updated eigenvector. Okay, and after this update, sorry, this is the update. After this update, we only use the diagonal entries of this updated estimator sigma naught, together with the well-behaved off-diagonal entries from the sample covariance matrix. Together, this the summation serve as the newly updated sigma naught estimate. We call it sigma naught hat T. And then we do this iteratively until convergence. Okay. So questions so far? And I know the algorithm is a little complicated.
So for the U is like the first K column of the eigenvector, right? So the U. Okay.
This is U. Yeah, this is the initializer. I will talk about the initializer later. So let's assume we have some reasonable initializer.
Okay.
Yeah. So the algorithm only needs this guy.
Okay.
Okay. So I want to highlight some critical steps. Although we also have the thresholding procedure, but here the thresholding procedure is different from the thresholding procedure proposed for the homoscedastic Sparse PCA. If you remember, so previously I mentioned in the Sparse PCA with homoscedastic noises, the thresholding level is a uniform thresholding level, the same. But here we have heteroskedastic noises. So it doesn't make sense. We still use the uniform thresholding level to threshold each entry, because each column here may have different noise level. So we propose to use so-called the noise adaptive thresholding level. Again, the gamma naught is some constant, say this is 2, and the sigma max we will discuss later. So this is the largest variance for the noise matrix. Okay. And lambda k, of course, is the kth eigenvalue of the low rank matrix, but we assume lambda 1 to lambda r are comparable. So those parts are comparable for each entry. So what makes different is the sigma j, right? So that means for each row, the noise level can be different due to the heteroscedatic noises. So here we propose to use adaptive thresholding level instead of the uniform thresholding level. Okay. As I promised, we come up with some initializer for the leading eigenvectors. This is needed for the power method, right? But as we discussed earlier, for power method, we only need a very general initializer. As long as the initializer is not orthogonal to the truth, we should be good. That also applies to the scenario in our model. So we don't need a consistent estimator of the U, as long as the initializer U is not orthogonal to the true U, we should be good. So because of this very mild requirement, we consider so-called off-diagonal sparse PCA as how we initialize. So if you look at the covariance matrix, the sample covariance matrix is equal to a sparse low-rank matrix plus a diagonal matrix. So that means actually the entire covariance matrix of X is also sparse, right? So we can take advance of this sparsity structure. We do entry-wise thresholding procedure for each off-diagonal entries. In other words, we start with sample covariance matrix, and we look at each off-diagonal entries and we do thresholding. Of course, the thresholding level also depends on the variability of each sample covariance matrix. So here we propose to use so-called also called adaptive thresholding. And then for the diagonal entries, we know that they're sparse, so we simply use the diagonal deletion scheme. So we know that diagonal deletion scheme is not good because it's still sparse, but hopefully after deleting those diagonal entries of the sample covariance matrix, the bias can be alleviated so that the resulting estimator based on this off-diagonal thresholding procedure is not orthogonal to the truth. Okay, so in the end, we just do the SVD, okay, based on the diagonal deleted sample covariance matrix and the off-diagonal thresholding procedure. And the leading eigenvectors serve as our initializer. Okay. Questions about the initializer? Okay, good. So that's the proposed algorithm, including our initializer. So we want to talk about some theoretical guarantees. So this is the to quantify. Okay, this is the model we considered. Okay, generalized by covariance model. To quantify heteroskedasticity, the homostatic noises. Here we use the two quantities. The first one is the sigma max. Sigma max measure the largest noises for the among all coordinates of the noise vector. And also we use the sigma sum square to denote the aggregated the noise only on the support of the eigenvectors. Okay. I want to mention that for the homostatic spec covariance model, so all sigma 1 to sigma p are the same, right? So sigma max square is it's just equal to each one of them, and consequently the sigma sum square, of course, is equal to the cardinality of the support, say little f, times the sigma max square. So of course that means this guy is always larger than the sigma max square. But in our heterostatic case, the sigma sum square can be even smaller than the sigma max square, because the sigma sum square will only count those sigmas on the support, and the max can be outside the support, so that this can be even smaller, larger than the sigma sum square. This can be very different. Right. Okay, and we need a few conditions. I will explain those three conditions carefully, and then hopefully you will see that our conditions are very mild or kind of minimum or even necessary. As I mentioned, the first one is imposed on the incoherent constant. The incoherence constant, the range of this guy is between 1 and p over r. R is constant and p can grow very fast. So here we only assume the incoherence condition has a very mild upper bound. We allow the order of the incoherence constant as large as p over r, but with just a small constant ci. Okay, and the second condition is imposed on the signal. We assume all the signal for lambda 1 to lambda r the same order. Of course, this can be relaxed. So we need this condition just for the simplicity, or our result will look neater. And also, if you look at Sparse PCA literature, this is well assumed. I think most people assume this condition. Okay. But instead, we don't assume the relationship between the noise sigma and the signal lambda. It can be there can be like any relationship between those different quantities. And the third condition is imposed on the sample complexity. So there are two parts, and the first part we assume the log p is over n is small, and that makes sense, right? So p can be very large and even can be exponentially large compared with n. And the second requirement is imposed because later we'll see actually this is the optimal rate convergence. That means the requirement here is necessary if we want to get some consistent estimation. If this is violated, then there's no estimator which can achieve consistency uniformly. Okay. And the second sample size requirement actually is stronger than this part times this part. And actually this is needed for our initial estimate. And later we'll see actually this requirement is nearly necessary. In other words, if this is violated, so there's no computationally feasible algorithm which is also consistent. So we talk about that later. So in other words, we impose very mild condition on covariance constant on the signal levels, and our sample size requirement are kind of necessary or minimum. Okay. So under our conditions 1 to 3, so we get upper bound for our initializer. You see that our initializer, the upper bound has two parts, and the second part actually is a constant. So that means this upper bound is useless if this is our final estimator because this can be inconsistent. Okay, but as I mentioned, we don't need consistent initializer as long as our initializer is not orthogonal to the U. In other words, if this guy is strictly smaller than 1, we are good, right? So we only need impose this constant is sufficiently small so that this upper bound is smaller than 1. Okay. And then together with the property of our initializer, we can show that after, roughly speaking, log n number of iterations, okay, our algorithm based on the power method can achieve this upper bound. Okay. So we have seen this upper bound in our sample size requirement. Actually, this is later we'll see this can be further improved. So we show that this will hold with high probability. Okay. So how should we understand this upper bound, right? So we consider a special case, right? So of course, our model also includes the homoscedastic PCA as a special case in which we assume sigma 1 squared to sigma p squared is the same. If that's the same, then our upper bound can be rewritten because we know that sigma sum is square root of the sparsity of the support times sigma max for sigma. So upper bound becomes this way. And actually, this is the well-known optimal rate convergence for sparse PCA problems studied in the literature. In other words, if our model is homoscedastic PCA, our algorithm still can provide the optimal rate convergence. Okay, but if we look at the general case and we define S tilde as the ratio of sigma sum square over sigma max square, our upper bound can be written like this, which is quite similar to this upper bound for the homoscedastic PCA case, except that we replace the sparsity S by S tilde. Because of this, we can view this S tilde as the effective sparsity or effective dimension, intrinsic dimension for our homoscedastic sparse PCA. Right? But as I explained that, due to the definition, right, S tilde can be even smaller than 1, far less than 1, because the sum is only defined on the support of those coordinates, and while the max is defined on the whole diagonal all the considering all coordinates. So if we follow the analysis in our proof, actually, if we don't use adaptive thresholding in the thresholding procedure, but use some uniform like thresholding procedures, we at most, or the best we can get the result with this S tilde replaced by S. Okay, because S tilde can be much smaller than S, so that means we will get suboptimal estimation. Okay. Another thing I want to mention about the computationally lower bound. Actually, in the low literature of sparse PCA with homostatic noises, people realize the proposed computationally feasible algorithm always require a stronger sample size requirement. For the special case, becomes the same one we imposed in the condition 3, the second part of the condition 3. In other words, if this condition is violated, the people show that the problem, sparse PCA problems, can be coined as the hidden clique problems in the computer science community. And we know that if this is violated, then we are in a regime that there's no computationally feasible algorithms which can give you a consistent estimator of the sparse PCA problems. Okay. Because of that, we assume we would say this condition is merely necessary, or it's not very strong. We further justify our upper bound by providing a matching lower bound. So we consider the parameter space, which is exactly the same conditions we imposed in our upper bound theory. So we assume the parameter space consists of all those kind of covariance matrices, can be written as the diagonal matrix and the low rank matrix, and we assume all the eigenvalues of the low rank matrix are comparable. We assume the largest noise is bounded by sigma max square, and the aggregated noise on the support is bounded by sigma sum square, and also we impose the same mild coherence constant. Then we will get nearly matching the lower bound. Okay. The lower bound and the upper bound are actually the same. Oh, sorry. Yes. Okay. So combining this upper bound and lower bound, we can say that actually our proposed algorithm is minimax optimal. All right. I still have some time, right? Okay. So we go over some numerical studies. So we consider the heterostatic noise variance sigma 1 squared to sigma p squared can be generated in this way. So first, we generate uniform distributions v1 to vp, and each sigma I squares actually is proportional to vi to the power alpha. Right? You see that the larger the alpha is, we have a more spread out variance sigma 1 to sigma p. So we consider the single spec case, the R is 1, and also we consider the multiple spec case, for example, k equals 3. Okay, and we because height marginality, we assume the n is large. Sorry, the p is larger than sample size, and we just present the case p is equal to 2n. So in our draft, we consider more general relationship between p and n, and also we assume sparsity. The s is only 0.1 times the dimensionality p. Okay, and this is the performance of our proposed method together with many competing methods, either in sparse PCA literature or in the low-dimensional heteroskedastic PCA literature. Okay. So the behavior of our algorithm is denoted by this solid line in black, while all other methods you see that has like worse performance compared with us. I want to skip this part and talk about some the application. But just to mention that we questions.
Yes, a quick question. So you compare different methods. So who implement these methods? Your one person implement all these methods, or you use other people codes? In terms of implementation.
Right. Yeah. For most of their proposed algorithm, there's a package in R, so we just use their package to do the implementation.
Okay.
Okay. And this is the performance for the multiple PCA case. And again, our performance, our procedure is better compared with others. So the x-axis is the alpha. As I mentioned, the larger the alpha is, the we have more heterostatic noises. So at the beginning, when alpha equals 0, actually, this is the homostatic noise case. So our procedure may not be the best. Okay. But as alpha goes larger and larger, and the advantage of our procedures is more significant. Okay, and also we just look at some plots to see whether the finite sample performance of our procedure is match the upper bound, optimal rate convergence upper bound, and we see that this is indeed the case, right? So when 1 over lambda is small, then essentially that means this is linear, okay? This part is linear. And when 1 over lambda is large, actually we see that the second term is okay. So this matched the optimal rate convergence. So we applied our method to a single cell RNA sequence data classification problems. Our data is from the Baron et al. The cell paper. So there are nearly 2,000 the cells based on the transcript abundance. Okay, and actually there's in total there are 13 clusters. So in other words, we assume we know the ground truth of the cell type, actually based on their unique transcript of each cell. Okay, and there are nearly 15,000 genes. That is the P, the number of dimensionality, and then we consider the most pancreatic islet cells. Okay, so actually we didn't use all the data because it's not very easy. I would say due to the computational burden, we just randomly sample 500 cells, and we only not random sample the genes. We pick the most significant genes using the existing R package. We only pick the leading 2,000 genes. Okay. So together with our dimension reduction method, we apply many other cutting edge dimension reduction method used in the single cell RNA sequence data analysis, including the t-SNE, SOMAP, factor analysis, ICA, like non-negative matrix factorization procedures. So we consider all of them. So we apply each dimension reduction procedure to the data, and we reduce the dimensionality only to fix the number of components, and the number goes from 1 to 10. And based on this reduced dimension variables, we do the k-means to do the classification. And here we use the normalized mutual information to measure the classification error. Okay, so the darker means the better, or the larger the normalized mutual information means the smaller of the classification error. So the performance of our proposed method is the first column, and the third column is the Heteroskedastic PCA algorithm without taking into account the sparsity. And the last one is the t-SNE performance, because t-SNE only allow us to extract the 2 or 3 components. So that's the reason we only demonstrate the case with 2 components. We see that overall that the heteroskedastic PCA and the heteroskedastic sparse PCA provide more satisfactory classification results. And in particular, if we further take into account the sparsity in high dimension, then our performance is even better than the performance by the heteroskedastic PCA. That means at least for single cell RNA sequence data, as the heterostatic noises has to be taken into account because it's a common phenomenon. Right? So this heat map shows the potential advantage of our algorithm in the genomic study. Okay, I don't have time, but I just want to mention that our heteroskedastic sparse PCA can be extended to the sparse heteroskedastic sparse SVD problems. So if you look at the matrix denoising problem, so if we observe the noise matrix X, actually which is written as the low rank matrix S, deterministic matrix S plus some noises. So here, if the variance of each noise have different variance, so we can consider the gram matrix of the noisy observation X, and our target is the left singular vectors of this low rank matrix S. Then if you look at the expectation of the gram matrix, and the off diagonals is unbiased, while the on the diagonals is biased. Okay, so that makes our algorithm applicable to this scenario. Actually, in our draft, we also provide rigorous theoretical guarantees for these sparse SVD problems with heterostatic noises. Sorry for the extra time. Let's take a quick summary. So in this talk, we consider the sparse heteroskedastic PCA problems, and our proposed method are based on the generalized by covariance model. So we don't need the strong signal assumption. We allow any relationship between the signals and the noises. So our procedure is rooted from the very simple power method with the modification using the adaptive thresholding step together with the diagonal imputation step. And also we propose the matching lower bound to show that the proposed method can achieve the minimax optimal rate convergence. And also we talk about some future, the extension of our procedure to the sparse sparse SVD problems. I think that pretty much all about the talk. Thank you.
Great. Yeah, thanks, Zhao, for the great talk. So now, any question from the audience?
I have two questions. Thank you for the talk first. And one question that I have is for the thresholding. You were using, I think there was sigma max in there. So how do you estimate that to use the thresholding while you are performing it?
Right. Actually, yes. In our algorithm, we assume we know that. Of course, those are unknown to us, of course. So in practice, we cannot use this so-called oracle thresholding level. So in our draft, we actually propose some practical way to give some estimator of sigma j and sigma max, which is based on our initializer. Okay. So you know that our initializer, we have this guy, and we take the SVD and use all the eigenvalues as the estimator of the sigma 1 to sigma j. Actually, we consider that case. Actually, this is the last page. So if we use that, the rough estimator of lambda 1 to lambda j, sigma 1 to sigma j, and then we plug in that in our algorithms, so we still can achieve the optimal rate convergence, but we need a stronger assumption. So this result comes with some price. Okay, so with this additional assumption, this assumption is related to the relationship between the noise and the signal. Okay, so our estimator is kind of consistent in the sense that the ratio is bounded below and above. So this guy still works. You see.
Oh, okay.
Thanks.
Thank you very much.
What's the second question?
Well, if other people don't have questions, I will ask that one too.
Okay. Sure.
So I think at some point you assume that the sigma i's don't have any relationship with the scale of the signal. So sigma
Yeah.
I and lambda. But
true.
in some questions
we don't yeah.
we have like sigma I scales with the scale of the signal. So how would that change the results here and the convergence?
That's a good question. Actually, we don't explicitly assume the relationship between the sigma and the lambda and the sigma, right? But implicitly, we impose some relationship. We assume this upper bound is little one. Right. Yeah. In other words, that for example, if you look at this ratio cannot be too large. Right? This ratio has to be smaller than square root of n over log p. So actually, implicitly, we impose some conditions. That means that the noise cannot be too large compared with the sigma. Yeah. So again, as you said, if they scale the same, then this ratio essentially, I think what you propose is the sigma is scale the same as the root lambda, right? Because sigma squared is the noise. So then that means this becomes a constant where the sparsity left, right? So that gives us to a simpler rate convergence, let's say the square root of the intrinsic sparsity or effective dimension times log p. That gives us a neater upper bound.
Thank you very much.
That's for the clarification. Yes.
Simon, go ahead. Yeah.
Hi, thank you for the great talk. So I have a question about kind of maybe I'm missing something, but I'm not sure. Like, so based on the basic power iteration, right? So typically the ratio between lambda 1 and lambda 2 will determine the speed of convergence, right? For example, if they're really close, the power method will converge very slowly. So, but in your theory, these ratios do not seem to appear in the theory. So I was just wondering, yeah, if they play any role. Okay,
right.
They change the constant.
That's a good question. Actually, we assume the initializer is not orthogonal to the truth. Actually, we assume there's some gap, any constant gap. So as long as there's a constant gap, so the bias due to the iteration actually evolves a geometric. So that's the reason. Sorry, that's the reason.
Okay, so there's a constant. Oh,
we need
a constant gap. Okay.
Right, we need a log number. Yeah. So there's a geometric decay. So it's very fast. But in practice, I agree. Sometimes it's faster, sometimes it's slow.
Yeah. Okay. Thanks.
Okay, sure.
Great. So if there are no any other questions, we'll have let's thank the speaker again. Thanks, Zhao. It's a great talk.
Okay, thank you.
Yeah.
Thank you, Ian, for that.
Okay.